No matter what parameter we're interested in, if we want to calculate a confidence interval for that parameter, this confidence interval is going to rely on what we call critical values. Now, critical values are going to be specific values that come from some reference distribution, and specifically it's from the sampling distribution of the statistic that we're interested in. And what they allow us to do is calibrate the specific confidence level for the confidence interval that we're interested in. So if we want a 95% confidence interval, we're going to use different critical values than if we want a 90% confidence interval or a 99% confidence interval. The idea with critical values is often seen with a few different distributions. So for instance, we might look at the critical values of the normal distribution, but the underlying concept is going to hold no matter what distribution we're dealing with. And the distribution that we deal with depends on what the sampling distribution in the given scenario is. So nearly every confidence interval is going to rely on a critical value from some reference distribution, and the concept that gives you critical values is going to hold no matter what that reference distribution actually is. So if you think about forming a confidence interval in a normal population for the mean, then this is going to require normal critical values. And so specifically, these are frequently denoted with this Z alpha over 2 notation here. And what we mean by this is that if you take Z alpha over 2 and you plug it into phi here, and phi is the cumulative distribution function of the normal, then Z alpha over 2 is the value that's going to give alpha over 2 out. Right? And so specifically what we're thinking about here is that it's matching this alpha over 2 with the probability. And so in other words, Z alpha over 2 is the value that there's an alpha over 2 probability that the normal is less than that. The standard normal falls less than that value, right? And so the critical value is defined in this way. You could also use the opposite critical value, the Z of 1 minus alpha over 2, and that's going to sort of come from the other end of the distribution there. Now, crucially, the critical value is actually a population percentile or quantile. We can sort of use those words interchangeably. And all we mean by that is that the percentile or the quantile is going to be the value that if you plug into the CDF, you get some set probability out, right? So here we wanted alpha over 2 as the probability. So it's whatever value we can plug into our cumulative distribution function to get alpha over 2 out of it. So the key focus for this lesson is to really understand what critical values are. Where are they coming from? What are we actually talking about when we're dealing with critical values? And then again, these lessons are going to apply whether we're dealing with a normal distribution or if we're dealing with something that looks very non-normal, right? The same underlying concepts apply. So in order to find critical values, we very rarely are going to be doing this by hand. It's almost always going to rely on tables, which will just have a whole lot of critical values printed on them, and then we can look up which one we need from there, or else from computers. And in sort of modern times, the very most common way you're going to grab critical values is through the use of statistical software. Just about any statistical software is going to do, but we'll look at how we can do that using the R programming language, because that's the most common way that we're going to actually be doing this within statistics itself. And so it's sort of a good skill to learn. Even if you're not actually programming, being able to run some of these commands becomes very useful. Now, the actual critical value depends on the level that we're looking at, right? So this alpha over 2, if we had wanted a different value for alpha, right? If we plug in 5%, it's going to give us a different critical value than if we plug in alpha is 10%, right? So the critical value we're looking at depends on the level, but it also depends on the distribution. And specifically, we're thinking about it depending on the distribution through this CDF that we're thinking about here, right? So this phi here is because we're looking at the normal. If we weren't looking at a normal, we would need to do something else here exactly. Okay. Now, what I want to do is actually look at what are we thinking about in terms of critical values through sort of discussing percentiles and discussing the distributions itself. And I really want to try to do this visually because I think that's sort of the way that's going to stick best in our minds here. So if we draw out what a normal distribution roughly looks like, right, we're going to have something like this. We can draw in our axis here. Right, and then the normal density curve is our bell curve shape. We can just sort of roughly sketch it out. Whenever we're sketching out our distributions, it doesn't need to be a perfect sketch, right? The whole idea is going to hold no matter what. And remember, if we want to find any probability from this distribution, the way that that's going to work is we need to look at areas under the curve, right? And so specifically, if we wanted to know what's the probability that we fall between, say, two values, we put an A here, we put a B right here, right? So what's the probability if we call, say, the random variable here x? What's the probability that A is less than x, which is less than or equal to B? This probability is given by however much space is under the curve here, right? So it's this whole shaded area here. And this is going to be true for any event that we might be interested in, right? So if we had moved B around, then it's going to be the probability would be wherever B moves to, but it's still going to correspond to that area under the curve. And so very often when we're dealing with any type of inference problem, it's going to be quite useful to start with our sketch and really try to think about what probabilities are we actually thinking about here, okay? And when we're dealing with critical values, all we're doing is actually thinking about sort of one specific type of probability that we might try out. So I'll leave that there, and we can come and take a look at sort of a newly drawn normal distribution here. Okay, and we'll put in the curve right here. Again, it's always fine for it to be just a very approximate curve. So if we want the critical value that corresponds to the value of alpha, right? So we want the alpha critical value. When we're dealing with the normal distribution, we would refer to this as z of alpha, right? If you're dealing with a different distribution, you might use a different letter here, but the idea is that it's just going to be some reference to the distribution here, right? And so the idea is that z of alpha is going to be the value such that the probability that x is less than or equal to z alpha is equal to alpha, right? That's the probability that we're actually looking for. Now, because x is normally distributed, right? So x is a normal 0, 1. The probability that x is less than or equal to any value is actually exactly equal to phi of z alpha here, right? And so this gives us that same relationship we were looking at previously, where we take phi of z alpha equals alpha, right? And so that's mathematically the quantity that we want here. But what are we actually saying sort of graphically? Well, we're going to take z alpha to be some value here. Say, we'll put it on the plot there. And what we want is the probability that x is less than or equal to this value to be equal to alpha. And so how do we think about that event of x being less than or equal to the value? Well, it's going to be everything under the curve up to and including that line there, right? So this whole shaded area here, if we want that to be a probability of alpha, this whole shaded area needs to be a probability of alpha, right? And so the critical value is going to be the value that puts alpha probability there, okay? Now, if you think about thinking of another critical value, so we want, say, z of 1 minus alpha over 2, right? We're still going from the normal distribution. Well, we can sketch out what this is going to look like, right? So we put in our normal plot here, draw out our density, okay? And so what we need now is we need 1 minus alpha over 2 to fall under this critical value. So we can come in and we can say that, well, maybe the critical value is about here, okay? And so what's this probability? Well, the probability that it's less than or equal to this is going to be given by all of this here. Okay. And so then what we need is we need this red shaded area to be 1 minus alpha over 2. Now, of course, because we know that the whole shaded area has to be equal to 1, right? The probability that it falls anywhere is exactly equal to 1. What we're also saying in this example is that if we shade this upper area in blue here, then this has to be equal to alpha over 2, right? So we can think about it as either putting some weight above our critical value or below it. If it's below it, then it corresponds to whatever the actual critical level is. So in our case, that's 1 minus alpha over 2. And so then it has to be 1 minus alpha over 2 below it. But you could also think about, well, you can put the complement above it, which in our case is alpha over 2. Right? And so then thinking about this first example up here, we could have also said, well, that means that there's going to be 1 minus alpha over 2, probability above it. Right? And so with these graphics, the critical values are always going to be the point that puts some set probability in the lower tail. Okay? And so by doing this, what we're able to do is control sort of how much probability there is in extreme events, and that's going to give us sort of a basis for the confidence intervals that we're interested in. Now, because these critical values depend on the distribution as well as on the actual level, there's always going to be different specific numeric values that come up depending on the distribution that we're looking at. Now, the most common critical values that we'll be dealing with sort of in any statistical inferential problem are going to be the normal critical values. And so they're worth taking a look at and actually sort of becoming comfortable and familiar with. So they come up sort of all over the place, and you'll start to learn sort of at the common levels what these critical values actually are. So if you take alpha to be 0.005, then that's going to give you negative 2.58 as your critical value, right? So Z of 0.005 is going to be negative 2.58. Z of 0.025 is 1.96 or negative 1.96, and Z of 0.05 is negative 1.64. Okay, so these are 3 very commonly used critical values, and those are the specific values that we're actually thinking about here. And so then if we just take a look at that first value, then what we're saying, right, is if we draw out sort of our rough distribution here, sketch it in very roughly, it's saying if we take a value that we put down here at negative 2.58, right, then everything below the tail here, this is going to give us 0.005 probability, right? So the probability that we're in that shaded area is 0.005. If we're looking at the negative 1.96, right, so we come somewhere around here, right, and then we take a look at what is in this shaded area. In that shaded area is going to be 0.025. Right, so that's what we're saying with these critical values. And that's true of any normal distribution or any standard normal distribution, right? It's always going to be the case. Now, the normal distribution is symmetric, and so we actually can say something about the lower and the upper critical values. And so, in particular, the magnitudes of Z alpha and Z1 minus alpha are always going to be equal. And so what we mean is that if you were to take the complement probabilities, then you're going to get the same values across the different critical values. And so we can write those out here, right? So Z of 0.995 is equal to the same critical value in magnitude, but the opposite sign as Z of 0.005, right? And so what we're thinking about here is if we have alpha equals to 0.005 in our first example, right? Well, then 1 minus alpha is 1 minus 0.005, which is 0.995, right? And so then by conclusion, we're saying, well, Z of 0.005 is going to be equal to the negative of Z of 1 minus 0.005, right? And this is going to hold for all of the normal distributions, right? And so then if you take 0.025, then that's going to correspond with 0.975 and so forth. And the basic idea here, all that we're saying is that we have sort of our normal distribution right here, right? And if we consider, say, some level down here, right, which we'll call Z of alpha, right? So we put alpha down here. Well, we saw with the previous diagrams that if you wanted to find Z of 1 minus alpha, you're going to be putting alpha above it, right? And so we can come in and put Z 1 minus alpha over on this side, and that's going to have alpha up here. And then because there's a symmetry to the normal distribution, that's going to actually be the same distance away, right? So this distance right here is equal to that distance right there. All right, so that's what we're saying by this. But what this means practically for us is that if you have the critical value for 2.5%, that's going to give you the same critical value as for 97.5%, right? So these critical values are the same. It's just one has a negative sign and one has a positive sign. Okay. Now, the other piece here is that if you don't have these memorized, then we can actually get them from statistical software. And so in particular, thinking about R, we can use our qnorm function to find the normal critical values. So qnorm is of 0.005 is going to give us the z of 0.005. Qnorm of 0.975 is going to give us z 0.975. Qnorm of 0.0127 is going to give us z of 0.01827, right? And so these values are going to be output here, right? And you can see they're sort of a little bit larger than what we have, or a little bit more decimal points than what we've recorded here. Typically, you'll see these reported to sort of 2 decimal points, but in R, you'll get sort of the full value there. Now, I'll point out that this qnorm function, what we're actually sort of asking for with it is we want the quantiles of the normal, right? So the Q stands for our quantile, and the norm gives us for the normal. And so there are going to be plenty of other Q functions, right? So we'll have Q and then other stuff here. And if you fill in sort of the other distributions there, that's going to give you the quantiles of those distributions as well, right? And so for the normal, it's not going to take very long to memorize 2.58, 1.96, and 1.64. But for other distributions, they come up a lot less. And so using R to grab those critical values is going to become sort of a very useful tool, right? And so feeling comfortable with doing that will be great. Critical values are going to show up no matter what confidence intervals we actually are looking for, no matter what confidence intervals we need. Right? No matter the distribution we're looking at, the critical values are going to correspond to the same idea. And so if ever you're in doubt about what a critical value is, think about drawing out the sketch of the distribution, think about where you're putting that alpha level, and then by thinking through it in that way, you'll sort of never be misled about what these critical values are. If you need the actual critical values for reference, you can either turn to a table of these values, or you can turn to R or a similar statistical package in order to actually determine the specific value so that you can use those to calculate the confidence intervals or do whatever other inferential procedures you need to do.